First topic 3 by Prof, and he will tell us about degenerations of rational maps.
Thank you for the invitation. Thank you for the introduction. So the idea is in these three talks is to talk about non-Archimedean techniques. So for short, NA techniques to study degenerations of rational maps. And to explain a couple of applications of these techniques. So I would like to discuss a proof by G and Xie about Macmillan rigidity theorem. And also I'd like to discuss how to use these techniques to understand how the multipliers of periodic points blow up. Okay, so there are many other applications of these techniques. So there are recent very impressive papers by many people, some in this room. So Laura, Myrto, Yap, and also Pilgrim, Nie, and Luo. I'm not going to discuss these more advanced topics. I'm going to focus on these two applications. Okay, so what is the principle? So it was developed by also many people. I should cite Yan Kiwi, again, Laura and Kurt. So you start with a sequence of a rational map that induce the dynamics on the Riemann sphere. They all have the same degree, d, at least 2. And what you want to, you're interested in how the dynamics of Fn degenerate when n tends to infinity. And what we're going to do is to attach to this sequence another dynamics, Fna, Na for non-Archimedean, that will live on P1, but not necessarily over C, over some new field. Let me call it K. K will be a norm field, which will be non-Archimedean. And the idea is to study the dynamics of this new dynamical system, which is over this strange field, and from the studying of this dynamics to infer some interesting properties about how, for instance, the Julia set or the Fatou set degenerate for Fn. Okay, so that's a general principle. And so what I'm going to do today is to describe how this principle works in the case of families, the holomorphic families. Where the field here is quite easy to describe. And in the second part, we're going to do some non-Archimedean dynamics. So we'll need to understand a little bit, so I suppose that you know a lot about the dynamics of a rational map on the Riemann sphere. And so we're going to do the same, but now for a rational map defined over acting on the projective line over some non-Archimedean complete field. Okay, so now I'll try to discuss as many examples as possible during the talk. Okay, so what is the holomorphic family? So I'm going to consider one parameter holomorphic family, parameterized by the unit disk in the complex plane. So let's say D star is a puncture unit disk. So we're going to consider not a sequence, but a family Ft, parameterized, let's say, by the puncture disk. So Ft is a rational map. So it is a holomorphic family of degree D rational map if it is a quotient of two polynomials, Pt of z over Qt of z, where P of t is polynomial whose coefficients are holomorphic in T. Same for Q. And I'm going to assume that for T non-zero, they do not have any, okay, so sorry. So it has, the FT has to have the degree D, so the maximum of the degree of P of T and Q of T has to be equal to D. And for T non-zero, I want P of T and Q of T to have no common factor. Okay? So when T is equal to 0, I allow us to have some degeneration. It could be that P of 0 and Q of 0 have common factors so that the degree can drop when T is equal to 0. Okay. So the main two examples I'm going to, well, probably you have to keep in mind is the following one. So you can look at your family, the family of polynomials of quadratic polynomials, of degree 2. So, sorry, I don't hear anything because of.
Can you just say what again this intersection is? What do you mean by intersection?
GCD.
Okay.
They do not have any common factor such that FT has real degree D when T is non-zero. Okay. So here it has degree 2, and so what's happening when T is equal to 0? Basically, everyone is mapped to plus infinity, to infinity. Okay, plus or minus doesn't make sense. The second family I'd like to keep in mind is so-called Macmillan family. Okay, so let me look at ZQ plus T over Z square. I hope it might be that I switch the degrees afterwards, but whatever. So this is a family of degree 5. And you see that when T goes to 0, what happens? It's that you degenerate to a family of degree, to a polynomial of degree 3. Okay, so this is so-called Macmillan. So when T is what's happening when T is very small? The Julia set of this is a counter dust, okay? And when T is very small here, it's a counter family of circles that are all nested. I'm not going to draw this on the blackboard. Okay, so let me go on. So you have your, you take your favorite holomorphic family of rational map of degree D, and then I'd like to describe which field is going to, which non-Archimedean field is going to appear, and what is this non-Archimedean rational map here. So it's kind of a recipe. So what you do, so Ft is P of T over Q of T, and you see that here, what you're going to do is you're going to interpret this holomorphic function as an element of a new ring and a new field. So you interpret the coefficient A of T, AI of T, and Bj of T as elements of a new field. Okay, so A of T is, as I said, is a holomorphic function. So you can take the ring of holomorphic function and try to take the fraction field of the set of germ and so on. So, but what we're going to do here, which is more natural, is to embed this in the set of power series in T. So it's still a ring. And its fraction field now is a field of Lorentz series in one variable, formal Lorentz series. Okay, so this the field here is going to be that field of formal Lorentz series, and the same for Bj of T. And so when you have a holomorphic family like this, well, you can attach Fna. It's going to be a rational map. I'm not sure exactly how to write this down, but Pna over Qna, it's a rational map with coefficients in the formal Lorentz series. Okay. So as I explained before, what we want to do is to discuss the dynamics of this rational map. And so we need the field to have some topology. Otherwise, studying the dynamics on the one-dimensional curve is not very interesting. And it's exactly what I said here. So my field is going to be endowed with a natural norm. So what is the norm I'm going to put on this on the field of formal Lorentz series? This is a norm induced by the evaluation which sends a formal Lorentz series to the order vanishing or the order of the pole of the Lorentz series at 0. So in other words, whoops. So let's say you have an element, let's say H, in the field of Lorentz series. So you can look at its expansion. So it's a Lorentz series, meaning that you might have infinitely many coefficients, non-negative coefficients that are non-zero, but you have only finitely many coefficients with I negative, which is non-zero, right? So we start with I greater or equal to I naught, for instance. And so what is the norm, the t-adic norm? So you're going to take exponential minus the minimum of those indices I, such that hi is non-zero. Okay? So it's a norm. So what you can check is, so what does it mean for formal Lorentz series to have a norm less or equal to 1? It means that all negative monomials here have to vanish. So this is exactly the same as saying that H is in fact a formal power series. So in other words, the norm is bigger than 1 means that your formal Lorentz series has a pole at 0. Okay? Okay, and then I let you check that, so H1 times H2, this norm is multiplicative. The norm of a constant is always 1, except if the constant is 0. And it satisfies the strong triangle inequality. If you look at the norm of the sum, this is less or equal to the maximum of the norm of H1, H2. And why is it so? This is because this function here is in fact a valuation. So when you sum up to two formal power series, then it might be that they vanish exactly at the same order, and when you take the sum, then their sum is going to vanish at a higher order. It's exactly this inequality. Okay. So can also check that this field with this norm is actually complete. And this is the reason why I preferred working with the field of formal Lorentz series and not of converging power series. And so now, so we have this, the recipe. So we have a holomorphic family. Then we can attach to it a rational map defined over this non-Euclidean field. And the game now is to try to convince you that first we can understand quite well or develop the Fatou-Julia theory of the rational map over the field of formal Lorentz series, and then try to get one application, Macmillan's rigidity, to infer from this information some result in complex holomorphic dynamics. Okay. Yeah.
If you wrote formal power series or something, or
It's what?
if you wrote the field of convergent power series,
This is not convergent, this is formal here. Convergent usually is like this. But and this is not complete. Well, okay. Okay. Actually, this is a ring, but okay. Okay, so now I'd like to do some non-Archimedean dynamics. And so if you want to learn more about this, I advise you to read the book by Benedetto. He wrote an extensive book on the on these things. So I'm going to work in the following setup. So I'm going to fix. So you can always think as K being this field, almost. So K is going to be a field. This is going to be a norm. It's going to be complete non-Archimedean field. So non-Archimedean means this inequality is going to be true. And you know that, okay, some of you also like to work over R, but usually we work over C. We like to do that because it's algebraically closed. And here I'm going also to assume that this is algebraically closed. Okay, so then you can argue, this guy is not algebraically closed. Okay, fine. Just take the algebraic closure. But sir, it's not complete. Fine. So then you complete, and then you get something which is both complete and algebraically closed. So I'm not going to insist on that, okay? It's not really essential. But believe me, there are a lot of complete non-Archimedean algebraically closed fields. Okay? In fact, most of them are like this, whatever that means. Okay, so now I'm taking a Russian map, so a quotient of two polynomials, so of degree d. So the maximum of degree of p and degree of q is d at least 2. And the GCD is 1, so now we know what this notation means. And so this map induce, so we want to look at the dynamics induced by this map. On which space? Well, the first try is to look at the set of k points in P1. So what is this? This is just a k union infinity. And you have a natural map from this set to itself. Okay. Now the point is that in general, this this field here is not locally compact. It's never locally compact, actually. And so to develop the theory of Fatou and Julia without any local compactness, it's a bit hard. And so what we're going to do is, instead of looking at the action on that space, we're going to look at the action on a slightly bigger space, which is called, so it's natural. I should not say natural, but so look at the dynamics induced by F on a bigger space, which is called the analytification of the projective line over K, and that will contain this set. And here there are many ways in which you can analytify an algebraic variety, and we're going to use Berkovich analytification. So you're late. He was my student, so I can say, I can talk to him. Yeah, so 20 years ago, I would have spent 2 talks on describing the Berkovich analytification. So my plan is to spend 20 minutes at most on this, but okay, so there. Okay, so I need to, now I'm not going to, there are plenty of very nice references, and you actually have nice pictures about this space. So I'm not going to describe very formally what this is. but I'm going to tell you how to actually make computation in this space. Okay, still. So the Berkovich identification, this is compact. So I didn't define it, right? But you're going to see a picture in 1 second. So this is a compact topological space. It's also an R tree. It's a tree. By R, it's a complicated tree if you want. So what does it mean? It means that if you take any 2 points, X and Y, there exists a unique path, injective path joining X to Y. Okay, so there is no loop. It's a tree, it means it's one-dimensional and no loop. So this does not appear. Okay. And the other thing is that, so we have this classical points here, and these classical points are endpoints. Or the Berkovich identification. Okay, so yeah, okay. The formal definition is this. So a point in here is a multiplicative semi-norm on the ring K of T. So the spectrum of this is the affine line. And so if you take this, you get, in fact, the identification of the affine line over K. And so you have to also add the function that gives everyone plus infinity any polynomials of positive degree. Anyway, so what is important? Maybe I won't say exactly what this means, but okay, sorry, I forgot one thing. Whose restriction to K is the K norm, is the norm on the field. But what you have to understand is that if you give me a polynomial, then there is, since it's X and you take a point in the Berkovich identification, there is it's a multiplicative semi-norm on this. So it makes sense to take the norm of the polynomial on that point. So usually I'm going to write it this way. And this is a non-negative real number, possibly plus infinity if X is infinity. Okay, so then I said that I'm going to make some computations. And so I need to devise some tools to actually be able to make this computation. So what we're going to do, we're going to make a slight abuse here, and I'm going to identify points in P1 over K with balls in K. So what I'm going to explain is that if you take a ball, so what is a ball? Ball, it has a center and a radius. So here it's, oops, A is inside K. The radius is non-negative. So you look at all the points such that the norm, let's say less or equal to R. Okay. Maybe this is a closed ball. So I'm going to explain that a closed ball, define one point in the Berkovich identification. And you can think as the Berkovich identification as being the set of all closed balls. It's not exactly true, but we're going to work with fields for which this is actually true. Okay, so let me explain. So if you have a point, okay, whoops, and some non-negative real number, so I have this ball, and I'm going to attach a point, I'm going to write a zeta of AR inside the Berkovich identification. And what is its value on a polynomial? By definition, it's going to be the max, or we can, or the sup. The sup is always attained over that ball of the norm of P. Okay, so you look at all elements inside K in this ball, and you take you evaluate P at that point. Take the norm. It's non-negative real number and take the sup, like it's a max. Okay, and then you can check that, in fact, this thing is a multiplicative semi-norm. So this gives a point inside the Berkovich identification. Okay, good. So when r is equal to 0, what you get is just the, so you have only one point, just the evaluation of p at A. And so this point here is exactly the point in K. So when I say that, where is it? That P1 of K are endpoints of the tree, at least I explain why, okay, K is embedded inside the P1A, inside the Berkovich identification over K. Okay, so what is the picture now? Is that, so I said it was, the Berkovich identification is a tree. So we should see some geodesics or some path. And in fact, they are determined by fixing the radius here, the center, sorry, and varying the radius. So let me do like this. So here's r, the radius. You have 0, you have infinity, and here you have a set of points, which is supposedly k. And now what you can do, you can draw a path like this inside the Berkovich identification. So if this is, I don't know, A0, and this is R, it's going to be the point corresponding to the ball, closed ball centered at A0 and with radius R. Yep.
Can I interrupt you before
Yeah, you can.
Can you just repeat again?
It's very hard for me to understand because of the fans, I'm sorry.
Can you just repeat what did you say over there? Like, you take A and R, and then you try to...
Yeah, so this is a definition of a, so if I take A and R, I get a point inside the Berkovich identification, which is defined, so it's a multiplicative semi-norm on the set of polynomial, on the ring of polynomials over K. And its value on the polynomial is the supremum of the norm of the polynomial on that closed ball. I didn't check, yeah, sure, yeah. Okay, so I didn't check that this is multiplicative. It's actually a non-trivial, but this is true. Okay. So then, okay, so let me take, how many points? Too many, etc. I don't know why I did that, but okay. So then I have a bunch of lines like this, and what's going to happen is that they are going to join at some point here. So let me explain what this means. So A0 and A1 are 2 points inside K, they are different. So when R is very small, the two closed balls are different. But then at some point, for the radius R, which is exactly the norm of A0 minus A1, what is going to happen is that the two balls, so you're in a non-Achebian situation. So two closed balls, either they are disjoint or one is included into the other. And so when you take the closed ball of the center A0, it has to contain A1 and vice versa, and so they have to be actually equal. Okay, so that's why you have this this kind of picture. Okay, so I mean it's not a proof that this is a tree, but and infinity is there somewhere there. Okay. Then let me come back to my rational map now, defined over K, and then you can show that F induces a continuous map, let's say by duality, on the space of balls or on the Berkovich identification. So it's going to be continuous. And it has a lot of very nice property, just like over the complex. It's, if you want, it is a finite cover, so it's finite map. And more than this, so on the complex, if you take a point, you can define its local topological degree. And here you can do the same. So you have a function which I denote by degree index f, which takes a point and map it to an integer 1 to d. So it's a local topological degree. At a point. And you have the nice formula that if you sum the local topological degree over the preimage of a point, you get always the same integer d. The complex, it says that your map is a ramified cover, and here it's exactly the same property. So for any, let's say, y, the sum over all its preimages of the local topological degree at x is constant equal to d. Okay? Okay, so now I want to introduce some basics in Fatou-Julia theory. So the natural thing to do would try to copy what the definition of the complex is, starting with normal families. One can do that, but it's not the way I'm going to introduce the Fatou and the Julia set. So remember that I remember that my advisor was Nessim Siboni, and so he's always using potential theory from. And so I'm going to do exactly the same. I'm going to construct a measure and define the Julia set as being the support of that measure. Okay. And then I'm going, yeah, you're not very happy, but this is the way I'm going to do. So, so we're going to build an equilibrium measure. So I didn't attend the first part of your talk. Did you already define it? Oh, no. Okay. So we're going to define an equilibrium measure. So it's going to be a probability measure. Sorry?
Thank you, because I will use tomorrow.
It's a probability measure on the Berkovich identification. And the Julia set is going to be the support of this measure. And the Fatou set, the complement. There are other ways to define the Fatou set and the Julia set, but I'm going to use this measure for other purposes, so I decided to define it this way. Okay, so so what I need is to define this measure, I need to have a pullback operator. So if I have a probability measure on the Berkovich projective line, what I want, so I can, since f is continuous, I can push it forward. What I'm going to do is I'm going to pull it back. So to pull back measure, it's possible because f is finite. It's a finite ramified cover. So it's the same as push forward functions. And so if you have a phi, let's say continuous functions on the Berkovich projective line, then you can push it forward. So at a point y, it's going to be the sum of over all its preimages. And here you put the you multiply by the local degree. So if you do that, then you can show that this guy is also continuous. And then the supremum is less or equal to d times, since the sum of the local degree is always d, this is always d times, bounded by d times the supremum of phi. And so by duality, you get a pullback operator. On measures. And for instance, if you take a delta mass at some point, let's say a point y, just by looking at the definition, this is going to be the sum of delta masses at all preimages of y, multiply again by this weight. This is local d. Okay, so the mass of the pullback of a probability measure here is multiplied by d, the sum of local degrees d. Okay, so then you do some potential theory. So you start with so what is this? This is an operator, just like over the complex. So you take a subharmonic function, you can take its Laplacian. This is going to be a measure. And here you can do basically the same. So I'm going to be very vague, but you have a set of functions with suitable convexity properties. And you're going to be mapped to Borel measures, so on the Berkovich identification. And this is mapped to Borel measures of mass, of total mass 0. And in fact, this is 1-to-1, up to constant. Okay, so I'm not going to define very precisely what this means, but this has the formal property, the same formal properties that the Laplace operator on the Riemann sphere. So if you take the Laplacian, if you take a rational map, let's say phi, you can look at its norm. So when phi has a pole, then it is plus infinity. When phi has 0, this is 0. You can look at its, the log of this. Then the log of the norm belongs to this class. You can take the Laplacian, and what you get is the sum of the order vanishing at points inside P1 of k of phi and delta mass at x. And then there is another computation that is important for what to follow, is that if you look at the Laplacian of the log of max and 1 and norm of t, so over the complex, this is a Haar measure on the unit circle. And here what you obtain, this is the analog. This is a delta mass at a point minus delta mass and infinity. And what is xg? In fact, this is what I denoted by zeta 0, 1. So this is called a Gauss point. So over the complex, you have exactly the same formula, except that this is replaced by the Haar measure on the circle. So the Haar measure on the circle is a very nice measure. It has local continuous potential. And so here what you see is that you have delta mass at a point, at a ball of positive radius. It has to be thought of as being a very nice measure also. Okay. This is Laplacian of some continuous function. Yep. Okay. So now how do you define this equilibrium measure? So what you do, so you start with the delta mass at this point, you pull it back, you divide by d, so this is a probability measure, and now you subtract by the delta mass at xg, and playing around with this kind of formula, what you can show, and this is a Laplacian of the log. So remember, f is, let's say, p over q. And so this is kind of an explicit computation. So it's Laplacian of 1 over d logs of max of the norm of p, norm of q, divided by the max 1t to the power d. So this is a function here. Let me call it G. Which can be checked to be continuous. And so now, so this is after one step, and now you can play it back n times. Whoops. And so you have some kind of, so you can write, so when you apply the operator 1 over d f pullback, then you get the Laplacian of G composed with f divided by d. And you can take the sum, you have a telescoping series. And at the end of the day, what you get is the Laplacian of the sum from, let's say, j equal to 0 to n minus 1, 1 over d to the j, G composed with fj. Okay, and so since G is continuous, and here what you do is you compose with something, but the supremum of this function is bounded, is uniformly bounded, and you divide by 1 over dj, and so this converges uniformly to some continuous function. Let me call it G infinity. And you play around with the properties of this operator, and that means that this measure, this sequence of measure here, converge to measure, I'm going to define as being the equilibrium measure. Okay. So this is exactly the same proof as over the complex. So what are the formal properties of this measure? Just by definition as being a limit of pullbacks, it is invariant, but it has a very strong invariance properties, invariance by pullback. So that is let me just write this. Yep.
Yes. We just had a naive question for accelerated growth. So you start with a rational function phi. Yeah. You want to compute the function at log at log. So yeah. So you extend phi as a function on the identification. Yeah, if you want that. But then it's infinite from all balls containing balls.
No. No. The function is in fact, what's going to happen is that, okay, so I didn't make a mistake. What I did was to define the value of a polynomial on a ball. Okay, so that's true. So if you have a rational map, you write it as a quotient of two things, and then you look at the difference of the quotient of these two things. And this makes sense. It's going to be finite.
Okay, and at the end, when you write this formula, the poles are only.
So the poles are on here. The poles are only are classical points. Classical point. Okay. So you have if you take, for instance, phi is equal to t, you have 1, 0, one pole at infinity. Okay. You have the geodesic joining, or the pi joining 0 to infinity. The value of, so log of norm of t is going to be minus infinity here, plus infinity here. And so this is a tree. So you have a lot of branches that comes off from this. And if on any of this path outside this geodesic, your function is constant. Okay? Okay, so yeah, so facts. So this, let me come back to this, the measure that we define here using potential theory. So this is invariant by pullback. So in particular, it's invariant by push forward. It's a probability measure, so it's non-zero. And you can also show that this is mixing. So in particular, it's ergodic. So it's kind of a formal consequence of the definition here. Okay. And so as I said before, so you can define the Julia set as being the support of this measure. and the fat to set as being the complement. And so just like over the complex, just like almost, the Julia set is, it's a compact set, sorry, which is totally invariant. And so here it's an open set, which is also totally invariant. And the dynamics here is essentially chaotic, and the dynamics here is regular. So, but you have to be a little bit careful. So here, at least what we know is that if you look at the topological entropy of the restriction to the fat to set, this is 0. And here I cannot say exactly that the topological entropy is positive, because it might happen that, in fact, this set is reduced to a single point. Okay, so yeah, of course, I'm very much behind what I plan to do. So still, I'm going to do one example. So I wanted to explain in the 3 examples what the dynamics is, but maybe I'll do that and so that you can understand that it's not so hard to make explicit computations. So, okay, so now, let me do some examples, okay? So I want to take K as being the field of Laurent series. But as I said, it's not so nice because this is not algebraically closed. So usually you embed it into a set of Puiseux series, which is not closed, which is not complete. And so then you have a smallest field, which is, we denote by L, which is both complete, the smallest field containing the field of Laurent series, which is both complete and algebraically closed. Sounds a bit crazy, but as you will see, I will stick basically to this field or sometimes to a Puiseux series also. So, okay, so what is the first example? Okay, I was looking at d square plus 1 over t, but let's look at d square plus t. Okay, so then you can, so what you can try is try to compute what is the image under the non-Archimedean polynomial attached to this guy of the ball of center 0 and radius r. So what is the normalization here? So remember that the t-adic norm of t is exponential minus minimum blah blah blah. So this is 1 over e. So this is less than 1. So how do you do to compute the image of the point attached to a ball? In fact, what you do is you compute the image of a ball. So if r is large enough, let's say r to the square is larger than 1 over e, then in fact it's not complicated to check that this is the image of the ball of center 0 and radius r is the ball of center 0 and radius r to the square. Okay. So get the point 0 here. You have the famous Gauss point. You have infinity. What I said is that so r to the square is bigger than 1 over e. Is okay, I don't know exactly, but so this is r is equal to 1 over square root of e. And so here this segment is mapped into itself, and the radius is mapped to r to the square. So in particular, the image of the Gauss point is the Gauss point. So this point here is fixed. So now what is interesting is to look at the local dynamics near this Gauss point. So we need to understand a little bit more what is the topology of the Berkovich projective line at this point. And so remember that there were, in my picture before, there were a lot of lines that were emerging at some points. So here the observation is that if you take, let's say, 2 points, Z and W, let me assume that z and the norm of z and w are less than 1, but that the norm of the difference is equal to 1. And if I look at, as before, at the set of points corresponding to the ball of center z and radius r, what's going to happen is that it's going to touch, okay, maybe I want here actually to be equal to 1. So I'm going to do the same for that point here. And what's going to happen is that they're going to merge this geodesic joining 0 to infinity exactly at the Gauss point. Okay, just like this. So you can, in fact, show that the set of, so you have a tree, so you can talk about the set of directions at a point, which is a set of segments modulo natural identification. So the set of directions at xg is in fact in bijunction. So there is one direction that goes off to infinity, okay, fine. And all the other ones are in fact in bijunctions with the set of points in K whose norm is less equal to 1 modulo this, okay, so it's not very clear, I'm sorry. Okay. I'm mixing a lot of things, so it's a bit confusing, I'm sorry. So here, in this picture, what I'm assuming is that norm of z is equal to 1, norm of w is equal to 1, and norm of z minus w is equal to 1. So what I wanted to say is that the set of direction at the Gauss point is in fact bijection with the set of points z inside K of norm less or equal to 1, modulo the identification where when 2 points are at distance strictly less than 1. So let me explain here. So in fact, so a priori, the set of direction is just a set, but there is some kind of miracle. It's because you're working with a non-Euclidean field. In fact, this set here, which is denoted by K naught, is a ring. And when you do this quotient like this, you mod out by a maximal ideal, which is a set of points whose norm is strictly less than 1, so that the quotient, in fact, here is the field. And so what's happening is something a bit strange, that this purely topological space, in fact, can be interpreted as the all elements inside the residue field, inside this field K tilde, where you join this point infinity. Okay, so the set of directions at xg is in fact in a almost canonical bijection with P1 of K tilde, which is K tilde union infinity. Okay, fine. So now what you can do is that, so we know that our non-Euclidean polynomials is fixing xg. So since it's fixing that point, it's going to act also on the set of direction here. And so you want to, if you want to compute the action on the set of direction, what you do is that you plug some z of norm 1, let's say random, and then you kill every term that have norm strictly less than 1. So here what's happening is that you're looking at f of z goes to z squared plus t, but this is a strictly norm strictly less than 1, so you kill this term. And so the map, in our case above, the map on the set of directions, which I'm going to write as Tf at xg, like a tangent map, is the map plus sin z to z squared. And so you see that this is a rational map, or okay, it's polynomial here, on this set of directions, on this P1 over K tilde. Okay. So then there are some formulas that tells you, okay, well, what is the degree of this rational map? It's 2. So this means that the local degree here of xg is equal to 2. And remember that this has to be, this is of degree 2. And so what you get here is that the pullback of the delta mass at xg is in fact 2 times xg, maybe plus extra points, but the total mass of this has to be 2. So it has to be, the pullback of delta of xg has to be exactly equal to this. So in particular, this point is totally invariant. And this implies that the equilibrium measure that I define here is actually equal to the delta mass at that point. So it's a bit strange, but you have an example where the Julia set is reduced to a single point. Yep.
Could you explain the reasoning behind why the tangent phase not is that?
Why this act like this? So I just explained that. So what is the direction? This is a point in K, okay, modulo this identification where the in K of norm less than 1, modulo the identification where the norm is strictly less than 1. So in fact, the recipe is you look. What you do is that you kill all the terms that are of norm strictly less than 1. And here I kill only this term, okay? It's not very formal, but in practice it works pretty well. Okay, so almost done. Maybe, yeah. Yeah, okay, let's do the next example. So ft of z is z squared plus 1 over t. So here we're going to see that the dynamics is more complicated. So just as before, fna of 0 of the point corresponding to the ball of center 0 and radius r. Okay, this is 0, the ball of center 0 and radius r to the square if r to the square is larger or equal to the norm of this, which is e. Okay, so now you have the following picture. So you have 0 here. So you have the point corresponding to the ball center 0 and radius square root of e. So the Gauss point is here right now. Okay, and so so this is mapped here, mapped there, and then goes off to infinity. Okay. So now what you can do is to look at the preimage of the point 0. So the preimage of the point 0 is, so f minus 1 in a of 0. This is z squared is equal to minus, okay, maybe I should have put minus here just to avoid complex roots. So it's 1 over square root of t or minus 1 over square root of t. Okay, so you see here 1 over square root of t is no longer a formal power series, but it's a formal Puiseux series. So so where are there these 2 points? So these 2 points are in my field L, and the distance between the two is exactly e to the square root of e. And so what's going to happen is that the geometry looks like this time. Okay, so now you can do a quick computation. Is that the ball fna of the ball of center, let's say 1 over square root of e, and of radius 1 is in fact mapped exactly to that point. So to the ball of center 0 and radius square root of e. Okay, so you have 2 balls here. Let's say U0 and U1. And this, all the set of points that are inside this set are mapped exactly to the ball here. And this ball here is mapped also to the yellow ball. So remember that a point has at most 2 preimages. And so here you have 2 balls mapped to the same ball. So it means that f and a map, let's say 1 to 1. onto the, let me call it V, this yellow ball. And it mapped also U1, 1 to V. And then I'm over time, but I'm just I'm going to finish like this. So when you have something like this, so it means that when you're pulling back this point, you get a point here and a point here, okay? And then you continue pulling back, you have smaller and smaller ball. And so in that case, the Julia set is going to be a counter set, and you have a canonical conjugacy to the set of let's say, so if you have a point in the Julia set, you can look at itinerary inside U0 and U1, and you get the conjugacy with the shift on two symbols. And so in this case, the topological entropy of the restriction of F to the Julia set is equal to log of 2. Okay, so it's a positive entropy. Okay, and then so tomorrow I'm going to discuss the third example, the Macmillan example, and then try to move on to general theorems on Fatou and Julia theory on non-Archimedean rational maps. Sorry. Okay.
Additional questions?
So where's the image of the gas point?
Yeah, so I should say right away on that this is so 0 is mapped to -1/t. So it's mapped to it corresponds to the ball of center of radius I don't know, and center radius 1 and center 1/t. So where is it? It's so the norm of 1/t is here, right? So in fact, it's in this picture it should be a ball which is here. And then it's shifted like this and goes off to infinity.
If we're to need to map the topological entropy can turn out to be anything different.
No, 0. Okay, for are you kind? Yeah, residual characteristic 0. Okay, so it's in fact in any residual characteristic, I think. Okay, I don't want to say so. Residual characteristic different from 2 is either 0 log 2 for here. And we're going to see, so not tomorrow, but after on Wednesday, that if the residual characteristic is 0, so this is, it contains the example of a field of Puiseux series, or formal Lorentz series over C, then the topological entropy is always the logarithm of an integer. But this is sometimes not 0 is not log of the topological degree. It could be something intermediate. So that's I'm going to discuss that. In the Macmillan family, this is log 2. So it's not log 5. It's not 0.
Any other questions? All right, let's make sure we're good.